Hey everybody. Today we're talking about the binomial distribution, which models the number of successes that occur in a sequence of identical random trials, each of which has only two possible outcomes. The simplest case is where you're only doing one trial, so let's get into that first to try and understand what's going on here a little bit better. We call this a Bernoulli trial, a probability experiment where there are exactly two possible outcomes, and traditionally we call those success and failure, and we denote the probability of success with the letter P. A few examples. Flip a fair coin and consider a head to be a success. The probability of success is 1 in 2. Notice, by the way, here that we could equally have considered a tail to be a success, so there's nothing logically necessary about a success, in air quotes, being a good thing and a failure being a bad thing. Those aren't mathematical words here. Another example, draw a card from a standard 52-card deck and consider an ace to be a success. There's 4 aces in that deck, so the probability of success is 4 in 52, or 1 in 13. Finally, suppose 40% of Americans approve of the President of the United States. Pick a voter at random. The probability of success in that situation might be 40% if 40% of Americans approve of the President of the United States. Now, we can view a Bernoulli trial as a discrete random variable by encoding a success as 1 and failure as 0. And this is frequently done, and it gives us this probability distribution. X can be 0 or 1. The probabilities are 1 minus p and p, respectively. Notice that those two probabilities add up to 1, as they must for any discrete probability distribution. The expected value here is going to be the sum of all of the possible values of the random variable weighted by their probabilities. So in this case, 0 times 1 minus p plus 1 times p. You do a little arithmetic there and you get p. And I think that's somewhat intuitive, that when you have a random trial that has a probability p of success, the expected value is p. On average, you expect to get a success p percentage of the time. The expected value for one trial is p. We compute variance and standard deviation in an exactly similar fashion. So for variance, for instance, we have the formula sum x minus mu squared times p of x, and that says take each of the possible x values, plug them in to this formula, and then add everything up. So for instance, when x is 0, we plug in, we get 0 minus the expected value, which is p, so 0 minus p. We square that, we weight it by the probability, 1 minus p. And then we do the same thing for x equals 1, plugging in there. We do some arithmetic, we add everything up, we get p times 1 minus p. We get the standard deviation by taking the square root of that, so square root of p times 1 minus p. Again, these are the variance and standard deviation for a Bernoulli random variable. Okay, back to the binomial distribution, which we abbreviate bin n comma p or b n comma p. And again, that's counting the number of successes in n independent Bernoulli trials, each with the same probability of success, p. Some examples there, similar to the ones we did before. Flip that fair coin 100 times and count the number of heads. So x is going to have a binomial distribution with parameters 100 and 1/2. Notice that x could take on any value from 0 to 100, but that values near 50, just sort of intuitively speaking, are going to be more likely. Second example, draw a card from a standard deck 50 times, putting it back each time before the next draw, and count the number of times an ace is drawn. So x is going to have a binomial distribution with parameters n equals 50 and p equals 1 in 13. Finally, contact 750 American voters at random, count how many approve of the President of the United States. So if the President has an approval rating of 40%, x has the distribution binomial with parameters n equals 750 and p equals 0.40. Let's do another example going a bit more in depth. Flip a fair coin 3 times and count the number of heads. So what I want to do is to get the entire probability distribution for x. So the most direct way to do that is to write out the entire sample space. This has size 8, and it consists of things like heads, 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 tails, etc. So to get the probability that x, the number of heads, is 0, I just look in that sample space and I say, how many outcomes have 0 heads? And there's only one of them out of 8 total outcomes, so the probability is 1 in 8. Similarly, the probability of getting exactly 1 head is 3 in 8, because if you look in that sample space, there's 3 possible outcomes that have exactly 1 head. Now, writing out the entire sample space and counting how many outcomes are in each of these events is a lot of work. It's manageable for 3 flips, but when you get into larger numbers of trials, it becomes unwieldy. So we need a better way. So let's get into some of the math here. We need to compute the probability that the random variable x, which has this binomial distribution with parameters n and p, takes on a certain value k. So k is going to be the number of successes that we're actually interested in. So k could be 0, 1, 2, 3, all the way up to the total number of trials, n. So if we're looking for a certain number k of successes, there's going to be n choose k ways that can happen, because you have n total trials and you need to put those k successes in there somehow. So n choose k ways of doing that. Now, for any particular ordering of k successes out of n total trials, you're going to have the probability of p to the k times 1 minus p to the n minus k. Because again, you need to have k successes, which have probability of p, and n minus k failures, which have probability 1 minus p. So, overall, the probability that x is equal to k is n choose k times p to the k times 1 minus p to the n minus k. Because we're taking the probability of any particular ordering, that's the second part of that, p to the k times 1 minus p to the n minus k, times the number of ways that can occur, so n choose k. And this is the formula that you use to compute binomial probabilities. For instance, suppose we have a basketball player that makes 78% of her free throws on average. And suppose she shoots 10 times. So we're talking about a random variable x that's going to have a binomial distribution, where x is representing the total number of shots she makes. So we have n equals 10. We're interested in the probability that she makes k equals 8 of the shots. So the probability is 10 choose 8 times the probability of success on an individual trial, 0.78 to the 8th power, times 0.22, the probability of failure on an individual trial, to the 2nd power. So again, we need 8 successes and 2 failures. Overall, we get 0.298. Here's one for you to try on your own. You should pause the video and before seeing my explanation. So she's still shooting 10 times, still has a probability of success of 0.78, but now I'd like the probability that she makes at least 8 shots. So the way I'm doing this is by finding the probability that she makes exactly 8, plus the probability that she makes exactly 9, plus the probability that she makes exactly 10. So I'm plugging in 8, 9, and 10 into the formula that I have a few slides ago for binomial probabilities. Adding everything up, I'm getting 0.617. A binomial random variable x can be viewed as the sum of independent random variables, all Bernoulli, each with the same parameters, each with mean p and variance p times 1 minus p. And so that can give us the expected value, standard deviation, and variance of any binomial random variable. The mean is n times p, the variance is n times p times 1 minus p, and the standard deviation is the square root of the variance. I think the formula for expected value here is pretty intuitive. If you have a probability of success p every time and you're trying n times, then the expected number of successes is n times p, the number of tries times the probability of success on each one. For instance, that basketball player shooting 10 free throws with a 78% chance of making any particular free throw has an expected number of successes of 7.8. 10 shots, 0.78% on each one, 7.8 shots made on average overall. We can compute the standard deviation by plugging into the formula square root n times p times 1 minus p to get 1.3. So on average, she makes 7.8 shots out of every 10 that she shoots. We're not surprised if she makes 1.3 less than that or 1.3 more than that. on average, her result will differ from 7.8 by that amount. As with any discrete random variable, we can construct probability histograms for binomial distributions. So here's one for the one that we've been looking at, for the binomial distribution with parameters n equals 10 and p equals 0.78. So for any x value on the horizontal axis, you can find the probability that she makes that many shots by looking at the height of the bar. So for instance, when x equals 8, we have a bar that is almost 0.3 tall. More exactly, we know that that bar is 0.298 tall, so that's the probability that she makes 8 shots.